So good morning to this, what is it, the sixth lecture, I guess, in CFD today. And today is just 1 hour because the second hour will be with the homework session. So what we will talk about today is stability, and we will look at the stability for an ordinary differential equation discretized with standard numerical schemes, in particular the Euler schemes. This is kind of a, how should I say, it's kind of a standard material in numerics or CFD, but it's very important that one kind of understands that and also understands the connection of the stability of an ODE to the stability of a partial differential equation. So, but maybe to just summarize and put everything into perspective with regards to what we discussed yesterday, I would just like to get back to this diagram that I have on screen, where you see the interaction between convergence, consistency, and stability. As we just discussed, convergence is the idea that the numerical solution, so my discretized velocity pressure field that I have, that this converges to the exact solution of the PDE, so that I get the correct result of my PDE. It's not that that my PDE is the correct physical equation. This week at that stage we cannot talk about that anymore. It's just about the numerical solution that comes closer and closer to the exact solution of the partial differential equation. Now, the exact form we did yesterday, and we wrote it down. So essentially, it's the difference, or a norm of the difference between the exact and the numerical solution. The problem is, in order to determine convergence, we would need to have access to the exact solution in order to calculate this difference, and that is not always possible. It is sometimes possible, and one of the cases we just mentioned, and that was if you try to solve, for instance, a linear equation system, then of course you know exactly when your residual is 0, then you have found the exact solution. So in that sense, you can define an exact convergence criteria. But if you think of time integrating Navier-Stokes, you actually you don't know that. You just have a bunch of different numerical errors, delta t, delta x, and you just want to know that if you grid refine, then you would converge somewhere. So therefore, it's very important for us to understand that we need to take a detour, and this is made possible by this Lox-Richtmeier equivalence theorem, which technically only works for linear systems without the boundary conditions, but yet it has been used for more complex or for different discretization schemes, even including boundary conditions. It's not fully rigorous in that case, and there may be situations that it kind of fails. But in the absence of exact convergence proofs for Navier-Stokes, this is as good as we can get. Note also that the Lox-Richtmeier equivalence theorem implies that you need to have a well-posed problem, which in fact is, even for Navier-Stokes, an unsolved issue, because there is essentially no existence and uniqueness proof for the solution. In any case, the way that we go is to show consistency and stability. Consistency, that is written here. There, the idea is that we do not consider the solution. We just make sure that the discretized equation is consistent with the partial differential equation that we want to solve. So that means that if we grid refine, that we recover the partial differential equation. That's the idea of consistency. And of course, as such, it absolutely makes sense that we need to have that we need to approximate the right equation. And then the third point here about stability, it means that my numerical solution approaches the exact solution of the discretized equation. And of course, that is only possible if I do not have a if I don't have a blow up in my iteration. And that means that in particular, all the errors that I have while solving the equation, and that might be errors that I get from truncation, that might be errors that I get from round off, so that I don't have exact arithmetics, that those do not grow and don't come in and destroy my solution. So that means consistency means I approximate the right equation, and stability means I actually get a right solution to this correctly approximated equation. And of course, this together, it kind of intuitively makes sense that this is then that convergence is given. Okay, so that's kind of the summary of last time. And what we would like to do now is to work a little bit more on stability of an ordinary differential equation. And we have already started with the Dahlquist equation, which was u prime is lambda u. U prime is lambda u, and this lambda was it was a complex number, so it was lambda r plus lambda I. And we have also found that the exact solution of this equation, so u of t is a times e to the lambda t. Okay, so now that we have this, we would like to see what happens if I do a numerical approximation to this equation. So I do a discretization. So I discretize with the Euler forward scheme. The Euler forward scheme is really the most straightforward numerical scheme that you could think of for the integration of a partial differential equation. It is just one-sided finite differences for the derivative. So in this case, it would simply give un plus 1 minus un divided by delta t is lambda times un. Note that I use the time level n and the time level n plus 1, and the right-hand side is evaluated with time level n. So that means that this is an explicit scheme. As we know from yesterday, if this is the case, we can solve this equation, or we can write an equation or a rule for each un plus 1. So un plus 1 is then 1 plus lambda delta t times un. So that's just solving this equation for un plus 1. And as we have used this the word or the terminology of an amplification factor, this factor in front of the u is exactly this g of lambda delta t. And as we discussed yesterday, is that this term g of lambda t times lambda, the delta t times lambda, this is a very important factor for describing this discretization scheme. Sometimes it's also called the characteristic polynomial of the scheme. Good. Now, what we need to do in order for stability to hold is we need to make sure that the amplitude or the absolute value of this g is limited. And the idea was we didn't want errors, linear errors in un to amplify over time. And what we saw last time is that the equation that determines the growth of epsilon, so the error, fulfills exactly the same discretized equation. So it's the same amplification factor also for the error. So epsilon going from epsilon n to epsilon n plus 1. Therefore, stability means that absolute value of this g lambda times delta t needs to be lower equal 1. so that the solution does not grow from one time step to another. So what we now need to do is to show or to analyze whether this is the case. Okay, so G should be lower or equal 1. Well, if we now fill in the expression that we have for G, that means that this is 1 plus lambda delta t needs to be lower or equal 1. And if we look at this, we can see that this lambda delta t, this is essentially just a complex number, which we can call Z. It's a complex number because we said that lambda is actually complex, and delta t obviously is a real number, so the time step is a real number. So lambda times delta t is just a complex number. Now, let's just look at this a little bit. What could that be? 1 plus lambda delta t, or 1 plus z. The absolute value should be lower or equal 1. Well, this essentially is a description of a circle in the complex Z plane. So this is the description of a circle in the complex Z plane. It's a circle where the center of the circle is located at -1 and the radius of it is 1. So if I sketch this, this is my complex plane. So here I would have the real part of Z, which obviously is the real part of lambda delta t, which is lambda r times delta t. And here I have the imaginary part of Z, which with the same reasoning is lambda I times delta t. Well, then this equation here is a circle with radius 1 at located at -1. So I have this -1, and I have a circle here. Right. That's not very nice. So, a circle at located at -1. Now the question is, what this is actually inequality. So stability is given if 1 plus z is lower or equal 1. So that means that's actually the inside of this circle where I have stability. So this is stable in a sense that the absolute value of G is lower or equal 1. Outside of this circle, it is unstable. Unstable in a sense that G is larger than 1, and that means that any error that you commit will eventually grow exponentially. Okay, so if you just write that down as a sentence, so the integration of equation 1, of course I need to say that this is equation 1, it would be this one. So the integration of equation, no, sorry, this would be equation 2, and equation 1 is actually the ODE that I had earlier. This would be equation 1. So the equation of equation 1 via the discretization in equation 2 is stable if Z, being lambda delta t, is within the hatched area, so the purple area. Of course, that's now interesting also to compare to the analytical region of stability that we have computed yesterday. But let's first analyze this for a second. So if we think that we have a specific equation given, so we have a specific lambda given, then it means that lambda times delta t needs to be chosen in such a way that I end up within this hatched area if I want to use the explicit Euler method. So if, let's just take an example, if I have lambda being a negative real number, so that means lambda times delta t is somewhere on this line. And that means for me that I just need to make sure that lambda times delta t is somewhere along the negative real axis. And that then clearly shows that I cannot choose delta t too large, because if delta t is too large, I will end up outside of the circle. So I get a clear limit of this value here, which defines me the largest possible time step that makes this system stable. At the same time, if my lambda is imaginary, so if we're along the vertical axis, well, then actually the situation is a little bit more difficult. It would actually indicate that there is no delta t that makes it possible to actually end up in the circle, except delta t being 0, because that's a circle that touches the origin just in 0, 0. So that means I cannot time integrate the Dahlquist equation if lambda is purely imaginary. That is not possible because it will always be unstable. If you have a general lambda, so just a complex number, then of course lambda times delta t would be a ray, maybe like this, and then you can scale the point along this line in such a way that you would then reach as the maximum time step exactly this the end of the circle. So that's the way that you should understand this point, this graph. So this would be lambda times delta t maximum. This point would be lambda, like lambda times delta t with delta t is larger than delta t maximum. And inside here, you would be at lambda times delta t with delta t lower than delta t maximum. So that's the idea of how to understand this plot. So what we can write here is that we have a clear restriction of the time step in exactly the way that I just explained, and this is actually very typical for explicit methods. You will do in homework number 2, you will do the same type of plot for a Runge-Kutta scheme, for an explicit Runge-Kutta scheme, and then you will see similar types of graphs. They will have slightly different shapes, but it's the same idea. You will have some area on the negative half plane, the negative real half plane, and the size and the shape changes a little bit depending on the method, but the basic idea is the same. Another interesting comparison is actually if you compare this now with the analytical region of stability that we have calculated yesterday. And there it turned out that everything here on the left side was actually stable. So this was the analytical region of stability. Well, what that means is that not all analytically stable lambdas can actually be integrated with the explicit Euler. Of course, that's an important thing to keep in mind. So not all analytically stable equations can be integrated in time via the discretization scheme number 2. Even though the original ODE would have been stable, would have led to an exponentially decaying solution, the time integration will lead to an exponentially growing solution. Okay, now maybe a side question here is, this was for the explicit Euler scheme, and we see this problem with that not all integration, not everything that is analytically stable can actually be integrated. Now, the question is, can we do something about it? Is there something that we can do better? And of course there is, and that would be the implicit Euler scheme. Yeah, so how would we write the implicit Euler scheme? Well, actually, it's very simple. It's un plus 1 minus un divided by delta t, and we have lambda times u, but now it's not un, it's un plus 1. So this here is the only change that we do for the implicit Euler scheme. And now, of course, we can calculate what the amplification factor is in this case. Well, we write it in exactly the same way. So we have un plus 1, but now it becomes a little bit different. It is 1 divided by 1 minus lambda delta t times un. So this here is the amplification factor for the implicit Euler scheme. So it looks very similar as what we have calculated up here in equation number 2. But it is slightly different. It's 1 over this, and there's a minus sign. Now we can call this equation number 3. Now the question is, if we also want to draw this here in a figure, again we have here the real part of Z, we have the imaginary part of Z. Well, what would that be? Well, it turns out, and can you please explain the last point again about the integration? Now I don't know what last point you mean.
The one before the implicit, you said that for the integration, it's not the last point that you wrote. Yes. Not
all analytically stable equations can be integrated via 2. Well, it means that there is a difference between the green hatched area, which would be this, so the whole half plane, the whole left half plane would be analytically stable in the sense that any lambda that I choose that has a negative real part is analytically stable, essentially meaning that it leads to an exponentially decaying exact solution. This you can see from here. So as soon as lambda has a negative real part, it would lead to an exponentially decaying solution, which in our definition of stability would mean it is stable. But now the explicit Euler scheme only allows you to do a stable integration within this circle. So that means there is points, so here or here or so, that are in principle stable analytically, but they're unstable when you integrate them via the explicit Euler scheme. What you have to do then is to essentially make the time step smaller, as I indicated here. So if you have this point, you just need to rescale it such that it actually ends up in the circle. But this is not always possible because points that lie exactly here on the imaginary axis, you can only rescale to 0, and the time integrating with a time step of 0 doesn't really help very much because you don't advance in time. But now what we want to do is we want to see whether there is an alternative, or maybe whether the situation gets easier by looking at the implicit Euler scheme. That's exactly what we try to do now. We have written here the the characteristic polynomial for the implicit scheme. So un plus 1 is 1 divided by 1 minus lambda t times un. And then now the question is to what shape that this corresponds to. And if you think about it, so again we need to do the absolute value of. So we need to do this. So g of z absolute value needs to be lower equal 1, and so you can just fill that in, and you then can calculate what it should become. It turns out that this specific g is also a circle in complex space. Now, because it's a minus sign, there will be the center of this circle is located on the positive side. The radius is still 1. It will be a circle like this. But because it's the inverse of it, it means that stability is actually on the outside of this circle. So that means everything that is hedged now is stable, and the inside of this circle is unstable. And now that's a completely different situation that we had before, because now it turns out that essentially everything is stable except this circle that is on the right on the positives on the positive axis. What it also means is that the complete analytically stable region, so the left half plane, is now stable. So irrespective of how I choose my delta t, as soon as lambda has a negative real part, so as soon as lambda delta t lies on the left half plane, I know I can integrate that stably using the implicit Euler scheme. And that is, of course, a very important property, because it means now I don't have to care how to choose the time step. I'm always stable. And that is, of course, very good. So if I so for the implicit Euler scheme, all lambda with negative real part are stable, irrespective of delta t, of the choice of the time step. That's actually an expression or a definition for that, which I just very briefly mentioned. It's not extremely relevant for us, but it's such a scheme that integrates everything, all the analytically stable values of lambda in a stable way is called an astable. It's an astable scheme, or an absolutely stable scheme. Stable scheme is a scheme for which all or for which the complete left half plane is integrated stably. And of course, based on this definition, we can now conclude that the explicit Euler, as most explicit schemes, is not absolutely stable or astable, whereas the implicit Euler scheme is astable. And again, that's typically true for all implicit schemes. So what we can conclude from that is that explicit schemes, they typically have a time step limitation. Implicit schemes do not. But what I also want to mention right now is that the accuracy on how you integrate those in time, the explicit and the implicit Euler, the accuracy is actually the same. Both of these schemes are schemes of first order. So the leading error term that we introduced last time is for both cases proportional to delta t. So that means the implicit Euler is not more accurate. It has the same leading error term. The implicit Euler scheme is just more stable. That, of course, also means that even though you could use larger time steps for the implicit Euler, so you can have very, very large time steps to do the time integration. But the problem is the leading error term is still proportional to delta t. So that the larger your time step is, the larger your error, of course, becomes. So that means it's not a solution to always take implicit methods and then time integrate with huge time steps. That will not give you an accurate solution because you still have a very large error in time. The solution will not blow up. Okay, fair enough, but it will not be accurate. Convergence, so the topic in the beginning, what we actually want. Convergence is still only achieved in the limit of delta t going to 0. So it means implicit schemes, they allow you larger time step, but it doesn't mean that you get a better solution. Of course, it will not blow up. So you will have convergence eventually, but the actual error may still be very large. So therefore, one needs to be a little bit careful with choosing too large time steps in doing a simulation. Even if the simulation doesn't blow up, it doesn't necessarily mean that it's a good solution. Of course, if the simulation blows up, then you know it's a bad solution. But not blowing up does not mean that you have no errors in the solution. Okay. Do you have any questions on this stability of an ODE? So how to assess the absolute stability of an ordinary differential equation? It is always the same procedure. You write the characteristic polynomial in kind of in the way that we have written here. So you have un plus 1 equaling 1 plus lambda t times un, and then you analyze the absolute value of this g. That's the typical way you do. Okay, you will have a homework where you try that, and you also find a nice MATLAB implementation of how to do these stability plots in a very simple and kind of straightforward way. Okay, but then we will go on, and we will start with the next chapter, which is actually to do this stability analysis for a partial differential equation. Now we looked at an ordinary differential equation, but the next step would be to consider that on a partial differential equation, and that is the so-called von Neumann analysis of a partial differential equation. Now, the history of this is quite interesting, and it actually goes back to the Manhattan Project in the Second World War in the US, where, as you know, a lot of scientists were kind of coming together and trying to understand some properties of, I guess, nuclear fission, and of course that involved the integration of partial differential equations in one way or another. At that time, the scientists then started to realize that you cannot just integrate, with whatever time step you wanted. That there were some limitations on it, and they wanted to understand what the problem really is. And of course, this was a very interesting problem from applied mathematics. And there were people like von Neumann But also, I guess, the first mention of this type of stability analysis actually doesn't come from von Neumann, but it comes from Crank and Nicholson, the two people that are important for the Crank-Nicholson scheme. But it evolved as a method for stability in the 40s and 50s of the last century. Now, what is the idea behind the von Neumann analysis? Well, the idea is actually very simple. We use a discrete Fourier transform, of the solution, and consider individual modes. Individual Fourier modes, and then you assess the growth or the decay of these individual Fourier modes. Now, I guess you directly see that whenever I talk about Fourier modes, there is, of course, certain limitations. The restrictions are that this is in principle only for linear equations. The linearity comes from the fact that you then want to consider individual modes, so linear partial differential equations with constant coefficients. In addition, we cannot analyze boundary conditions in this way. So that means that we also need to have periodic, or we can only use periodic boundary conditions. Otherwise, taking a Fourier analysis or a Fourier transform would not be a good solution. These are certainly restrictions to the von Neumann analysis, which also means that it cannot be formally applied in all circumstances. But nevertheless, it gives you a good idea of what the stability of a specific numerical scheme or a specific problem would be as a function of wave number. There is other methods, more advanced methods, which you can exploit the growth of energy in your solution, which then gives the concept of energy stability. And there's a strong school on that at Linköping University in Sweden, where they look at exactly this energy stability in various circumstances. So there is certainly more advanced methods that you can use for stability, but for kind of the purpose of an introductory course, I guess it's very important to also understand the von Neumann analysis or the Fourier method for stability. So how does it work? As I said, we do a Fourier transform. So that means we make an ansatz. We say that Ujn, so my solution at time step n and grid point j, can be written as a sum of uk hat to the time n times e to the I k x j. So what do we have here? So we have here two parts of this expansion. The first term, the u hat k with a superscript n, this would correspond to the Fourier coefficient, and that guy is dependent on time. So the time dependence of my solution is encapsulated in the Fourier coefficient, which I allow to vary as a function of time. The second part, so the e to the I k x j, this would be my base functions of the expansion, and these essentially are Fourier modes. So it's a complex exponential. So it's a sines and cosine, as we discussed, I think 2 times ago. But the interesting thing is that all the spatial dependence is encapsulated in the basis functions. So the Fourier, the sines and cosine. So all the space dependence goes here. So what we have actually essentially achieved by writing my solution as a sum of products of time and space is that we have achieved a separation of time and space. Then, of course, I also have here the sum. So I need to sum over all my Fourier modes that I have. And typically, if I think of a domain being discretized into n points, my wave numbers that I have are from minus n divided by half to n divided by 2. So I have essentially n complex Fourier modes. Now, of course, you see that there's a slight mismatch because I also have the 0 mode, so it's actually n plus 1. But let's leave that discussion for the moment. That's a slight complication when you actually implement it in a code. But the basic idea is that I just expand my solution in physical space into a sum of Fourier coefficient times Fourier basis function. And now, based on that, so that's my Fourier transform. But now I want to do to consider just one individual mode. So my individual mode, the individual mode would just be one of those terms in the sum. So u hat k at time n times e to the I k x j, and that is now what I would call as my solution. So this last expression here is what I would actually like to look at. And again, the reason why I can do that is because, so first I do a Fourier transform because I know I have periodic boundary conditions, so I can do a Fourier transform, and then I can take one individual mode because I think of a linear partial differential equation with constant coefficients, meaning that I can consider individual modes alone. And then the complete solution would be just due to linearity, a superposition of these individual solutions. Okay, so I have now extracted an individual mode, and what I would like to do now is to just look at the stability for these individual modes. So the requirement is that each mode on its own does not grow. And if I can show that for all modes, so I can show that all modes, all Fourier coefficients all Fourier modes do not grow in time, then I know that I have a stable scheme. But now I see that it's already 11 o'clock. So how to proceed here, we will consider next Tuesday, I think. Okay, with this, I thank you for today. And next hour will be given by Luca. And yeah, I wish you a nice weekend.